So we just introduced the Riemann tensor and different interpretations that it has. It came like this, and it's basically a measure of the non-commutativity of covariant derivative acting on another tensor, in particular a vector. Of course, the covariant derivatives do commute when they act on a scalar. And closely related to this, so we were going through different interpretations that the Riemann, or just started, I guess, different interpretations that the Riemann tensor has beyond this, which we could take to be its definition. And one that's closely related to this is that it's an obstruction to flatness. Or another way of saying it is that a region of space-time, let's say a simply connected region, to not worry about global topological issues, will be flat if and only if the Riemann tensor vanishes throughout that region. So how do we see that? So it's not only an obstruction to flatness, it's, so to speak, the obstruction, at least the only local obstruction to flatness. If it vanishes, then the space-time is flat. So how do we see that? So on the one hand, we're saying that if the space-time is flat, then the Riemann tensor vanishes. On the other hand, vice versa. So the first one is obviously simple. If the space-time is flat, so if, say, GAB equals A to AB, some flat metric, then that implies, well, we also gave an interpretation of the Riemann tensor as a holonomy, as a measure of non-integrability of parallel transport. So in other words, remember, it was the result, if you parallel transport a vector around some small closed curve, then it undergoes a rotation or a Lorentz transformation, and that Lorentz transformation is given by the Riemann tensor contracted with the little 2 vector that represents this area. So in particular, if the space-time is flat, then parallel transport is actually nothing. In other words, in a flat space-time, if you take the same vector v and you put it anywhere, it's in some sense the same vector. In any case, there's a unique meaning to calling it the same, and that's what parallel transport does. It just takes the vector into the same vector located somewhere else. By the same vector, I mean, if you like, that the difference between its head and its tail is a vector, and that difference is the same everywhere. So obviously, parallel transport along any curve at all in a flat space will bring you back to the same vector that you started with. And therefore, obviously, this implies that the Riemann tensor is 0, given this interpretation in terms of infinitesimal integrability, local integrability. Conversely, suppose, so that's trivial, but what about, how do we see that, suppose the Riemann tensor is 0, how do we see that the space-time is flat in that case, locally? Well, we can take, let's set up a local basis at some point in the manifold x0, which I'll call EA, say 1, EA 0, etc. You have this basis. Now, because this interpretation in terms of integrability, it means that we can, having set up the basis at some point, we can spread it to we can take it anywhere else in the manifold. So we've set up the basis at some point x0. We can get that basis anywhere else by going along some curve. And because of this interpretation in terms of local integrability, it means that it doesn't matter what curve we follow, right? We'll end up always at the same point. Okay, because you can see that any 2 curves, say 2 different curves, I can continuously deform the one into the other, and I'm assuming that I can do that, so that's a topological, if you like, a global topological restriction. I can continuously transform the one curve into the other, and then I can divide each pair of neighboring curves into little two-dimensional regions like this. It's not too clear in this picture. And then if you think about the integrability of parallel transport around each of these little plaquettes, then it tells you that the net effect of transporting along the first curve is equal to the same as transporting along the second curve, right? Because if I want to go, say I start with the first curve, and I want to convert that into the second curve, so I can, what I can do is go along this first curve for a while, switch over to the second curve, go back to the start, then go along the then go forward again, and so on. And in the end, if you work through what that means, it means that in the end, I'll have produced something where I go along the first curve, go back along the second curve, and back along, and then forward along the second curve. I think that's what you'll get. And that's clearly the same. What am I saying? Maybe I've got it the other way around. Converted the second curve into the first curve. But anyway, I can convert the two curves into each other by that method. I think I set it backwards. So if I want to switch the first curve to the second, then I go a little bit along the second curve, then I go over to the first, and then back, and so on. And then in the end, after that, then I push forward the place in which I switch, and at the end, I'm going entirely along the second curve, back along the first curve, and then forward along the first curve. And those last two processes, obviously, just by definition, cancel out, because parallel transport is reversible along a single curve. Anyway, so therefore, the result is that I'll get a set of vectors, I'll get a basis everywhere in the space-time, and those bases will be related to each other by parallel transport. So if I go along any curve in the space-time, starting with the basis vector I have there and take it over to the other point, I'll get the basis vector that I have there. So what that means, therefore, so then we choose this. We spread by parallel transport. That gives us a basis everywhere, a global basis. And then, by definition, it gives us a basis such that the gradient of A, of E, B, gamma, let's say, is equal to 0 everywhere now. And once you have that, then it follows immediately that the different basis vectors commute, right? So E, let's say A mu, A commutes with E, B nu, let's say. Why do they commute? Because remember, the commutator, or the mutual Lie derivative, I'm thinking these now as vector fields, so the mutual Lie derivative is just E between any two vectors. The commutator for two vectors is just the Lie derivative of one with respect to the other minus the opposite. And so this E, so it's equal to the E, but remember we had the formula for what the Lie derivative was, or what the commutator was. It's this. Okay, where I fill in the two vectors, mu and nu. Nu and mu, right? But since both of these terms are 0, the commutator is 0. That means that the two vector fields mesh, and that means that we can use them to form a coordinate system. We can deduce from them a coordinate system such that they're the basis vectors of the coordinate system. So if you want to know what the coordinate is, where is coordinate E0 equals 5 or something, then you just go along the E0 direction, a parameter length of 5, and if you want the others to be 0, let's say, the other say the pure time-like direction, then that'll bring you to some point, and then these will be the basis vectors of those. So if you think it's true, you will end up with a coordinate system, and in that coordinate system, the in the coordinate system, the metric will be constant because these vectors were parallel transport. So all their lengths and all of their angles are preserved by the parallel transport. So that means the coordinate basis vectors have the same inner product with each other everywhere, but the inner product of the coordinate basis vector is the metric component in that basis. So therefore we get a coordinate system, and it has the property that the metric components are constant. So that's one way of seeing it. So therefore the space-time is isometric to, or this portion of the space-time is isometric to a portion of Minkowski space. So it's isomorphic, at least in a portion, to Minkowski space. So it's flat. So the claim is, so that's the idea of the proof. So the interpretation here is that the Riemann tensor is an obstruction to flatness. It's zero if and only if the space-time is flat. Okay. So any question on that? As we mentioned last time, the space-time could fail to be flat globally. As a torus or something like that, or as many examples you can think of, where for global topological reasons, it's not isometric to a subset of Minkowski space. The simplest case is where you would just identify periodically in time, and then you would have a sort of a closed time-like curve, and of course in Minkowski space there's no closed time-like curves. So the next, and I think the last, or the next to last interpretation that I wanted to discuss for curvature is the geodesic deviation equation. This one is probably the most important from the point of view, from in respect of its physical applications. To see what's going on here, think of how you could. Remember, we talked about gravity being the everyday gravity is not being a reflection of curvature, and then ask what is a reflection of Riemann curvature. And I mentioned that it was what's called the tidal force. So what this means at an infinitesimal level is you could start two neighboring test particles, which are momentarily at rest with each other, that are at some fixed distance, and furthermore, they're momentarily at rest with each other. So that means that from the point of view of the space, say that they're free falling. So from the point of view of the geodesics, it means the geodesics are momentarily moving parallel to each other. So even though if you were in empty space, I mean, if there was no curvature, if you're in flat space, then of course you start them momentarily at rest with respect to each other. Then they'll just remain at rest with respect to each other. On the other hand, if there's curvature present, then in general they won't remain at rest with respect to each other. And the simplest way, this is what's called the tidal force. And the simplest way probably the simplest way of remembering it is to think of starting two particles at rest with each other in the Earth's gravitational field. So if they're freely falling, then they'll fall. And so to first order, I mean, if you neglect the curvature of the Earth, you won't see any change. They'll just fall, like in the elevator. They'll just remain still always at rest with each other and at the same distance. But when you take into account the fact that the Earth is curved, they're really both falling towards the center of the Earth. And so they'll start approaching each other slowly. So even if you were being held up by the floor and we were in free fall, if we started two particles at rest, then they would very, very slowly be drawn to each other. And there you're seeing the genuine effect of the curvature. in particular seeing that the gravitational field is not just given by some sort of uniform acceleration with respect to a flat metric. So that's what's called geodesic deviation, and it's important in many different contexts. But one of them certainly is in terms of what's called the Roy-Chaudhuri equation, which is a version of this geodesic deviation equation for whole systems of null geodesics, which are light-like geodesics. So an example would be the geodesic generators of a black hole horizon. That would be an example.
If the one is slightly closer to the Earth, then it will accelerate faster than move apart. Is that the same thing?
That's also, yes, right. That's also the same thing. So, yes, that's right. So, in fact, that's this kind of example. If there's no matter present, so that the Riemann tensor reduces to what's called the Weil tensor, which is trace-free. We'll just define it in a few minutes. But in that case, then you don't get you can't have something where everything is drawn together. That would be a spatial volume would be contracted. But all that you can have just from the pure gravity is shear. So in fact, the fact that so if we think starting them along a sphere, all possible orientations with respect to each other. If we start them this way, they'll be drawn together. If we start them this way, they'll be drawn together. But if we start them this way, as you say, they'll be drawn apart, and that actually better be so because you want the sphere to turn into an ellipse, but not to actually change its volume to first order. So that's known as shear. So yeah, exactly. Yeah. So they're all aspects, and in fact, they're intimately linked. So I want to just recall the setup that we've had a couple of times before for discussing neighboring geodesics or neighboring curves. One may be a variational situation. You want to deform this curve into this curve. In this case, we'll imagine them as both geodesics. So we imagine a real particle going along each of these, and we want to understand how the relationship between the two particles changes as you move along the geodesic, as time passes. So I'll just remind you of the notation we were using. So this was a curve gamma. This one we can call gamma plus delta gamma. Call the point on the curve x, and that's gamma of lambda, the parameter that we use to parameterize the curve, which is going to be, in a second, either proper time in the time-like case or affine parameter more generally. And then we had a second parameter, mu, which is the one that varied so lambda takes you along the curve, and mu takes you from one curve to the neighboring curve. And I introduced this delta x was a so-called connecting vector, and then dx, as in dx d lambda, is the vector, the tangent vector to, or is a sort of infinitesimal portion of one or the other geodesics. So we're imagining now a whole family of geodesics parameterized by lambda and mu, but one should think, in practice, mu is to be thought of as infinitesimal. Lambda is an affine parameter. And a couple of notations here. So this variation d, the one that takes you along the curve, is formally d lambda times partial lambda. And this delta notation, I'll call it delta mu. But the important thing, it's partial mu. Okay. So if you look at this equation, x equals gamma of lambda and mu, and you vary x in it a little bit, then you get, according to this rule, you get dx, which is partial x, partial lambda times d lambda, and so on. So these are just numbers, which you should think of as small. These delta mu and d lambda are numbers which you think of as small or infinitesimal. So as we just said, there's no, we're not going to get any, I mean, an example we just looked at, sorry, let's think of what kind of equation we should expect to get now describing how this connecting vector evolves along the geodesics. You can't expect to find a first-order differential equation for delta x because I can start the two geodesics anywhere and with any relative velocity. So I can make the rate of change to first order of delta x be whatever I like by choosing the relative velocities of the two particles. But once that's fixed, then the rest of their, the geodesic equation is a second-order differential equation. Once I fix the velocities, then the rest is determined. So we should expect to get some sort of second-order differential equation, if we're lucky, for the connecting vector. So that's what we're seeking. We're seeking the second derivative of the connecting vector with respect to affine parameter lambda. Okay. And I've written this big D. That's to remind us that we're using, when we, as always, if you talk about differentiating a vector from one that has to be compared from one point to another, you have to say how you do the comparison, and this is telling us that the comparison is done by parallel transport or covariant derivative. So a little more notation. We have UA, as we've usually done, I'll call the tangent vector to the individual geodesic. So that's just dxa d lambda, or I could call it partial xa partial lambda. That is, it's d by d lambda, which is a vector. And the A reminds us that it is a contravariant vector. So that's that. Okay. In the same way, the connecting vector dxa is equal to, just following along, the partial derivative of gamma now with respect to mu, and I'll give that a name. So here I've kept this finite. I'm thinking of this one as still small. So I'll keep the sort of infinitesimal factor here, prefactor, and I'll give that a name of V A. Okay, so the normalized connecting vector will be V, and the normalized tangent vector is U. And the normalization is by affine parameter in the case of U, and by this arbitrary parameter mu in the case of V. Now, remember when we did this last time, when we defined the two vector fields. So now we have two vector fields. Strictly speaking, we've seen this issue before. Strictly speaking, I've only defined them so far along a two-surface, and it might not even really be a two-surface because I could take degenerate cases where the geodesics cross or something like that. But anyway, let's ignore that issue. In the end, it doesn't make any difference. So we saw that in this case, so we have now two vector fields defined on space-time, and because these things mesh, in other words, if you go a parameter distance 1 in the mu direction and then a parameter distance 1 in the lambda direction, it commutes with doing them in the opposite order. You end up at the same point. That's by construction. Since they mesh, that means that their Lie bracket is 0, and that means this is where. So let's make one other definition. I'll write, this is the same shorthand we used before. I'll write for U, for the covariant derivative along the U direction, I'll just write it as grad sub mu. So this is what when we just go back to when we derived the Riemann tensor, we showed this is what we derived first, this equation. And if they didn't mesh, there'd be another term. But since they do mesh, there's no other term. This is for any arbitrary vector. Did I get that in the right order? Yeah, okay. So this is a general equation. Now let's apply, so just keep that in mind. Now let's work out the first, and let's work out the second derivative that we're trying to that we're aiming for. So remember that d by d lambda, that is equal to dxa d lambda times gradient a, or if you like mu dotted into, that's grad mu, because dxa d lambda is u, so it's grad u, I should say. So therefore, what we're interested in is d squared delta xa over d lambda squared. That's just applying d by d lambda twice, so it's just grad u times gradient of a, right? Now, here's the crucial, I didn't write this other crucial thing down, but so let's do that now. We've seen it before, but maybe it's good to write it down as well now. So the fact that these mesh, means that the Lie derivative of the one with respect to the other is 0. So we had this notation for the vector fields themselves. Their Lie bracket, as this is called, is 0. And the Lie bracket was grad uv minus grad vu, right? So that equals 0. So that means that we can switch the order in u and v. That's the crucial step, which we also, I think, used the same thing when we were deriving the geodesic equation the second time around. Okay, so that's the statement that they mesh. Now, let's apply this. Let me divide through, since it's on my notes. Let me divide through by delta mu and do this not for delta x, but for v. Okay. It's the same. They're the same thing. They're just related by this constant, by this. Where is it? Where? Somewhere. Oh, it's on this. It's yeah. Here it is, and this is just a constant which doesn't vary as you move along the two world lines. So I'll work with this, and now I'll apply that important thing. So I can now switch the u and the v in the first derivative, and now I can add and subtract something, namely grad v, grad u, to get ua. So I've subtracted it here, and then I'll have to add grad v, grad u, ua, right? Okay, so I haven't done anything except arrange these so that I would get a Riemann tensor. And this, again, since they mesh, again, we use this relation that we remembered here. So that's equal to, just copying from above, r a, b, c, d, u, b, u, c, b, d, plus, now we have to say something a little bit about this. This, if you remember, when we talked about the geodesic equation, this thing that I've circled is just dua d lambda, which we called, or which one calls, the acceleration of the curve. I haven't assumed anything being a geodesic yet. So in general, this is the acceleration. And so I can express the second term as the covariant derivative in the b direction of the acceleration, and that's the geodesic deviation equation. Although, well, maybe I should call it the not necessarily geodesic deviation equation. So this is completely general for any two curves so far. Where this, and I could, now I want to, actually what I want to do now is, just to express the meaning more clearly, multiply through everything by delta mu, go back to the connecting vector. But now if I do that, then I'll have to just a little bit. This curve was, remember, v dot del dot times the acceleration, but v was dx, that was delta x over delta mu dot del a. So, and I've taken away the delta mu, so I can just write the second term as delta x v grad v times a. I guess that's how I have it, right? So they're just equivalent forms, but this way is perhaps a little more suggestive because it shows you that this is the connecting vector. Okay, so this is completely. So, any questions on that? So this is completely general. Oh, I didn't started with the wrong blackboard. So this is completely general. Now, however, if we want the geodesic deviation equation, let's assume that gamma and gamma plus delta gamma and all these curves gamma of lambda for fixed mu are geodesics. Then it means, of course, it means by definition that, at least by one of the two definitions of the geodesic, it means that the acceleration is zero. If they're all geodesics, then A is zero everywhere, and so it's this is basically the derivative. It's the change in the acceleration as you go from one curve to the other. The acceleration is zero for both of them, so it's zero anyway. Trivially zero. So we can, for the case of geodesics, we can just cross this term out. Then we get what's called the geodesic deviation equation, but we're not quite finished. Because we haven't yet said anything about the parameter lambda. In fact, when I, where did it go? Oh. When I said that it was geodesic, when I said the acceleration was zero, that's not quite right. If the only thing I have to go on is that that the curve is a geodesic, it's only zero, right? If not only is if you remember how we defined the acceleration, which is right up here somewhere, it depends on how we normalize u, and the normalization of u, if we do it with an arbitrary parameter, then there's no reason that this actually acceleration will vanish. It won't. If you remember, the important thing is that the acceleration vanishes only if we normalize u such that lambda is an affine parameter. So we also have to assume that lambda, so not only that it's geodesic, but that lambda is an affine parameter. Under those two conditions, then this equation will hold with zero. But now there's something else. Let's think of the time-like case first. in that case, we know that we can, and normally we do, choose lambda to just be proper time. Or we might choose it to be something more proper time normalized by the mass, if you go back to that action principle that we had. But so we choose it to be normally, or we have to, in fact, we have to choose it to be some multiple of proper time. But then you might also want to, and so then this equation holds. But there's another thing that you might want. You might want this connecting vector to be a simultaneous connection. In other words, if you go into the rest frame of one of the particles and ask, where is the other particle? You might want to have the vector which tells you where the other particle is now, now in your frame. So in other words, you might want to require that. So let's take the timeline case now. You might want to require this simultaneity. But what does simultaneity mean? Remember, just from special relativity, two points are simultaneous with respect to some world line if the vector connecting them is orthogonal to that world line. Right? So this means we want orthogonality. So in other words, we might like this connecting vector to be orthogonal to u. And of course, that means also that it's orthogonal to u plus delta u, because that's a higher order thing. Or that's, if you make them infinitesimally close together, it's the same thing. So we might like this, or if you like, delta x and dx are orthogonal to each other. But then you could get into trouble. We've said two different things. We've said that lambda is an affine parameter that fixes it for all time once you set its initial magnitude, initial rate of change. We've also said that we want the connecting vector to be orthogonal to u, but the connecting vector is supposed to connect points by construction of equal lambda. So is that consistent? So fortunately, in the case where the acceleration is 0, fortunately that is consistent. So let's check that. And then we'll come to the light case. It's a little more subtle. But if it's consistent, then, if we set this up originally, then we're saying that the inner product, I'll just use this notation for the inner product of u and v is equal to 0, right? You can also read it as g of u and v. I just mean the metric inner product of u and v. That's orthogonality. Now, if that inner product is not preserved along the world line, then we'll get into trouble. But fortunately, it is preserved not only when it's 0, but always. So let's say d by d lambda, which is just little d by d lambda, because this is just a scalar whose derivative we're taking. So we don't have to worry about parallel transport. So that's equal to du d lambda inner product v. There's a g here, but remember this is the covariant derivative, so it. Well, no, let me write it like this. It'll be more clear if I write it like this. So that, I mean, I can also write that as grad u. Remember, everything, it's just acting on a scalar. That's equal to, now it's more clear that when this gradient acts on the g, you get 0, so we don't have to worry about it. So it's really GAV, UAU, VB, if you like. And then the second term is grad u v. Oops, I bunched two terms together. U times grad u v. This, however, is 0 because, remember, this is the acceleration, so we're assuming geodesics now. So it's 0. And we're left just with this term, but this is, now we play that trick again. So it's equal to u, that we can switch the u and v. So we get grad v u. Right? But now it's something symmetric in both arguments, and so it's just equal to the gradient along the v direction of u dot u with a factor of a half. Right? Okay. But okay, so we wanted this derivative to be 0. It will be 0. This, of course, means this just means 1/2. If I work out what that is, it's just 1/2 partial lambda, partial mu of u dotted into u with a little d. No, that's all it is. So this is just asking, how does u dot u change as we move from one geodesic to the next geodesic? So if they're both time-like geodesics from the same particle, then u dot u is always 1 or -1 or minus the mass squared or whatever it is that involves the mass, but it's just some constant involving the particle, and so that's equal to 0. Okay, so that's in the time-like case. So in the time-like case, u dot u is equal to constant, is equal to, say, -1, or I forget which way it goes now, m squared, I guess, or minus m squared if we use that normalization. But anyway, it's a constant that depends only on the particle. And so therefore its derivative is constant. So that's good. So now let's think about the light-like case. If we assume, so in this case, in the time-like case, there was no other hidden assumption, because if you infinitesimally vary a time-like geodesic, you get another time-like geodesic. So they both had to be time-like. However, in the null case, it's a little more subtle. If you infinitesimally vary a time-like, a null geodesic, light-like, it might not be light-like. But we'll assume that it is. So we're always comparing, say, a photon path with another photon path. That's the only case that I know of that ever arises in practice. So we'll assume all of these geodesics that we're talking about are all light-like. So we assume that u dot u equals 0 for all the geodesics. So another way of saying it is we'll assume that for all. In other words, I've assumed that the variation in u dot u is also 0. It's independent of this parameter mu that parameterizes the curve. Under that circumstance, under that assumption, then of course this derivative again, I've assumed just what I need to make this be 0. So it tells us that in either case, the inner product between u and v is preserved, so along the geodesic. So it means that the inner product, I'll write it out now, maybe in full, GABUAVB is preserved. Or if I write this in such a way that it reminds us it's the connecting vector, then that's preserved along the geodesic. So in the time-like case, it's natural, if you want, and it's natural to do, to resolve. See, there's an ambiguity. Even though in the time-like case we've normalized the rate of change, the rate of advance of the affine parameter, we haven't normalized the zeros. So it's like two clocks. They're both ticking at the, they're really ticking off proper time or some multiple of proper time. But we haven't said when they're set to be equal. So if we set them, but in the time-like case, it's natural to set them to be equal in this at simultaneous points in the reference frame of either particle, this orthogonality condition. The like case, however, is a little more subtle. It's subtle for two reasons. So in the time-like, we normally assume, so we usually do assume that this connecting vector is orthogonal to the tangent, and that we just seen that that's a consistent assumption to make. The light-like case is more subtle. It's in general not possible to make this assumption. If you think of two arbitrarily nearby geodesics, then it's not possible to do that because let's look at a 1 plus 1 dimensional case. So here are two neighboring light rays. Okay, no. So everything's flat, so nothing interesting happens from the geodesic equation, deviation equation. But now, can I find any connecting vector that points from one to the other that's orthogonal to u? Okay, so this is u. So in this case, what's the only direction that's orthogonal to u? U, right? U itself, u dot u is 0. You're not going to find another direction that's orthogonal to u because then the metric would be degenerate. But if I go along direction u, I'm not going to make it to the other light ray. So I can find many connecting vectors, but none of them are actually orthogonal to u. So we can't, so in the light-like, we cannot, in general, take u dot v equals 0. But we can take it to be, whatever it is, we see that it will be preserved. I mean, from this result here, we see that whatever it is, we'll take it to be constant. Now there's, for whatever interest that is, but some of the most important cases happen to be when u dot v is 0. And in that case, that's the one that's used, that comes up in the Roy-Chaudhuri equation for light-like vector. So what does it mean what does it mean if they are zero, if it is 0? It means, so maybe I should say we can take it to be 0 if and only if gamma and gamma plus delta gamma, the two geodesics, are what's called abreast. I think Roger Penrose invented this name, abreast. So it's hard to draw, but if someone, when you finish writing, if you could stand up, then I can illustrate what it means to be abreast. Okay. You heard, whoever. Yeah. Okay. Come. So we're both photons, right? So now the case that's drawn on the board is like this. So if you just walk at the same speed. Okay. So now we're not abreast. One of us is behind the other. Turn around. No, can you go? And now one is ahead. Okay. So that's not abreast. Either one or the other is right. But now suppose we walk like this. Right? Okay. This is called abreast. Whatever. Okay. So now between these two photons, the connecting vector would be orthogonal. Why? Because if I ask, what is orthogonal to me is my world line, well, I'm just repeating the same thing. But which events are orthogonal? It's those which are happening along either of our two world lines. Right? So neither one. The point is that the reason this couldn't be made 0 was that one is ahead of the other. If neither one is ahead of the other, then it can be made 0. I don't know. That's another, yeah. That's fine. If you draw a if you want to visualize it in terms of a three-dimensional example, the light ray would be some line running along this paper, and if you can easily work. Let this be sort of the z direction. Let this be the t direction, and let this be the x and y directions. Then, if I go off in the x direction, then the vector connecting has only an x component, whereas the tangent vector to the geodesic has only a t and a z component. So they're obviously orthogonal. And in fact, if you ask, what is a set of all vectors which are orthogonal to this tangent vector and begin on that vector, they just fill out the plane, okay, this null plane. So you get the whole null plane. As long as the two geodesics are on this same null plane, then they're abreast. And it means that their connecting vector joining them is orthogonal to them. On the other hand, if I had a second one plane behind one geodesic was on this, but another one on a plane that's parallel but away from it, then the inner product can't be zero. So it turns out that this case where they are abreast is of very great interest, say, in dealing with black hole horizons, the area laws and stuff like that relating to black hole horizons, because you have all these photons sitting on the horizon trying to get out to infinity, and they're not making it because they're being pulled back by the gravitational field, but they're running parallel to each other. Neither one is ahead. If one was ahead, it would get out, or the other one would fall back into the black hole. So another way of saying it is that the black hole horizon is a null surface. It's like this thing. And so all the null curves that generate it are in fact abreast. So if we ask for this, it turns out in the timeline case, you can always satisfy this, and there's one and only one solution for the connecting vector. In the null case, it's this typical situation where either there's no solutions when they're not abreast, or there's many solutions. Because if I add to it, if I take the connecting vector to be orthogonal, I mean, suppose there is a solution, and I take the connecting vector to be orthogonal to mu, then of course it's also true that if I add any multiple of the connecting vector, say r times u, if I add any multiple of the tangent vector to the connecting vector, of course that's still orthogonal to u, because u is orthogonal to itself. So it's basically saying that when we were walking side by side, although the connecting vector was going to be null, there was no objective invariant way of synchronizing our clocks. If you can call the clocks the things that pick off the affine parameter. So there's either no solution or there's many solutions, and that means that it's actually natural. What is unique, however, is the projection. The projection of the connecting vector along what I might call the projection along mu, which I mean you quotient out by this relation. That is unique. So in other words, it's natural to work, in this case, instead of working in the full tangent space of the space-time, it's natural to work in sort of, it's natural to work in sort of the orthogonal complement of u, which is not a complement in this case. It contains u itself. It's this plane, remember. It's natural to work in that. What I'll write like this: divided by u. In other words, where we quotient out by two vectors that differ only by multiple of u, we identify. So it's a typical kind of gaugey situation where there's a free, so to speak, gauge in the choice of this setting the zero of the clock. So that's and this is a two-dimensional. So that's where in 3 dimensions, when you come to the Raichandra equation, which is now relating many geodesics, not just 2, but a whole swarm of them. Then if you're time-like, then you consider all the swarm of all the particles around you. That's a little three-dimensional set. But in the null case, you only consider these abreast ones. That's two-dimensional. And then you find rules for how those, just like we were talking about, rules for how the shape of a bunch of my neighbors, how their shape that they form deforms as you go on in time. And in that case, they can get closer, farther, and they can shear. Okay. Okay, so just for lack of time, that's all. I won't go on and say any more about that, but that's the geodesic deviation equation. Okay, any questions on that? So now we want to get to, of course, we're heading mainly, above all, we're heading for the action, gravitational action. So let's consider tensors that we can make from the Riemann tensor. The first one is called the Ricci tensor. And that's simple enough. Let's write them in this order. So we start with the Riemann tensor. And then just contract these two indices. Could be these two, it doesn't matter. But by convention, let's say we contract these two. What you can't do is contract the first two indices, right? Because of the anti-symmetry in the first two indices, that will give 0. But you contract these two. I mean, there are more general gravity theories in which Riemann doesn't have this full symmetry. But in the case of metric gravity, which is what we're dealing with, it does. So you just contract this. And that's called the Ricci tensor, RAB. And then if you go further and contract these two indices, then GAB, RAB, that's called the Ricci scalar. So both of these are kind of traces of the Riemann tensor. The first one is a sort of simple trace, and the second one is, if you like, a double trace of the Ricci tensor. Now remember that the symmetry of the Riemann tensor was this. I won't actually fill in the letters here, but they have to be filled in appropriately. And so of course that's for Riemann. So that implies, just trivially, because one of the symmetries was you exchange the first pair with the second pair and you get back to yourself. So that implies that maybe I should fill them in here. CABB. So if I contract C with D, so to speak, what remains is A with B. Anyway, it's a straightforward, trivial observation. That implies that the Ricci is symmetric in its two indices. So it's a symmetric tensor. And then there's another thing that we can also make, which from these ingredients, which is called the Weil tensor. I won't write out its exact definition. It also depends on dimension. These definitions are pretty universal, and they're usually taken as the same definition no matter what dimension you're working in. In the case of the Weil tensor, well, remember the Ricci tensor was sort of a trace of the Riemann tensor, and the Ricci scalar was also a double trace. So in that case, you can ask, sort of after I form the trace, I've captured certain components of the Riemann tensor, but what about the ones that are left over? So that's the, so to speak, trace-free part of the Riemann tensor. What's left over after you know the Ricci scalar, Ricci tensor, and Ricci scalar. And the way to, and so that's usually called C. So it says, I'll just schematically show what it means. It means that there's some constant So what does this mean? It's a little, if you think of splitting a matrix into its trace, its pure trace and its trace-free part, like the Ricci scalar here, well, we can split, Ricci tensor, we can split it into a multiple of the metric and then whatever is left over. But in the first part, we'll carry the trace. Here, because there are more indices, you can take two traces. And so it's natural to split what's left over into two pieces. The part, and I left out the Ricci scalar itself. So there's the part coming from the Ricci scalar, which is then can only be a multiple of the metric. And there's some symmetrizations here, which I haven't, so I'll mention in a second. So you have to arrange this to give the symmetries of the Riemann tensor. And then there's the piece coming from the Ricci tensor, and it has to be arranged also to have the symmetries of the Riemann tensor. And then whatever is left over, which is not room for, which I didn't leave room for, is called the Weil tensor, usually written as C. And by construction, it will have no trace. So in other words, if I contract it on any two of its indices, it'll vanish. This thing, so now I won't bother with these coefficients vary from dimension to dimension, but this symmetry constructions are the same. So how can I make just from the metric, how can I make something that has the symmetries of the Riemann tensor? So let's say we think of it now as RA in this order, RA, B, C, D. So I have to have antisymmetry in C and D and also in A and B. So there would be no use in putting A, B here because it would immediately go away when I antisymmetrize. So I better put the B here, and then I'll put the C and the D here. Now it's got this nice, if I switch A with B and C with D, I get two minus signs, and that's good. It comes back to itself. But I need also to put the antisymmetry in C and D, for example. So if I antisymmetrize this in C and D, then you can check that it turns out it has all the symmetries of the Riemann tensor. So that's what this that's what this shorthand stands for. And in the same way here, now we have a little more. We have R, A, C, G, B, D. So we have only one metric and one Ricci tensor. So now we've got to do a little more. First, we can make this like it was before, like it was on the right, symmetrizing between R and G. Or if you like, it's symmetrizing A, C with B, D. And then second of all, we can symmetrize again in C and D. And that'll, again, you can check that that'll have the, this is symmetrizing, this is anti-symmetrizing. You will check that, you can again check that has all the symmetries of the Riemann tensor. And then what's left over, if you choose these coefficients appropriately to the dimension, will have zero trace, and that's called the Weil tensor. So now we've defined three tensors, the Riemann, Ricci, and Ricci scalar. So just as we tried to give some geometrical or physical interpretation to the Riemann tensor, the full Riemann tensor, we can ask about the interpretation of the Ricci scalar. So let's start with the Ricci tensor. So the Ricci tensor, it's some sort of remember, one of the interpretations of the Riemann tensor was it was this sectional curvature, the sort of Gaussian curvature of some two-dimensional subspace. In the case of the Ricci tensor, we can say something similar. Not too enlightening, maybe. But it's not a scalar, so it can't be directly interpreted as a Gaussian curvature. But if we contract it with some unit vector, say, we can interpret that as a kind of average sectional curvature. And if you set up a coordinate system in which this would be one of the coordinate vectors, then it's kind of the, or even if you don't, it's kind of the average of the sectional curvatures of all the planes that contain this vector. I won't bother. And then, yeah, so plane, this is, so it's average sectional curvature in planes. That means two planes containing this vector. And then the scalar is even easier. Just the scalar is sort of the average sectional curvature in all planes, if you like, you could say, for example, in all coordinate planes, giving any orthonormal basis. I guess you should say that because otherwise it's not going to be clear exactly what measure you take the average with. So since it's not that important, I won't write it out. But set up an orthonormal basis and take all planes like x, y, x, z, t, x, blah, blah, and average the, at least, well, actually, I'm not even sure about that. This might only be true in these statements that I'm making. I'm not sure. They might or might not be true in the Lorentzian signature, but they're true in the Euclidean signature. In that case, you can just average, for the scalar, you can just average over all two planes. I think a somewhat more interesting interpretation was actually found by Jan Meerheim and then rediscovered, I think, by Gary Gibbons and collaborator Solodukhin. And this is much more of a real space-time. That one, in fact, only, to my knowledge, only for sure works in the Euclidean signature. This one is definitely Lorentzian in nature, and it has to do with how volumes, so imagine a fixed point here. Take this to be a a time-like geodesic, and let its, as always, let its tangent vector be UA. And now go along this for a certain proper time tau. So this is a sort of, there's a second point along the geodesic, and it depends on tau. And now we take what's called the order interval between the initial point on the geodesic and this moving point, tau, that consists of all the points that are causally between 0 and tau. Okay. And so obviously, the volume of this will just increase as time goes on. So this is the volume. So this is volume V. That's a function of tau. And if you think how does it first behave? So if we were in flat space, this would just be the height of this sort of double cone, this order interval. And so it's just a linear scale associated with this region. And so, of course, we're in 4 dimensions, so the volume must scale as that linear size to the 4th. But then there's a correction coming from curvature, and the correction turns out to come in at the order t to the 6th, and it's some constant times the component of the Ricci tensor in the u direction, or the double contraction of u. Right? So this particular, you can take u to be any direction, and so in that way you can get all its components. So that's a kind of interesting interpretation, which becomes certainly relevant in the case of causal sets. So one last thing to say about the Riemann tensor is in general, you might want to know what are its components in a basis. So let's take the components. Let's go ahead. Let's take the components in a coordinate basis. Most of you will have seen that before, but let's just see how it follows from the definitions that we've given. So remember, of course, we'll be writing them in terms of these Christoffel symbols in that same basis. And remember what the definition of the Riemann tensor was. I'll do everything in the basis now, the covariant derivatives. I won't bother just to write all these parentheses after writing that. Henceforth, just imagine the parentheses. So remember, we defined the Riemann tensor in terms of the commutator of the covariant derivatives acting on a vector. So what we need is the anti-symmetrized covariant derivatives acting twice on the vector. So you can just expand all this out and see what you get. And we know that it must be of the form it must be of this form where I replace now u and v with indices, not vector fields. That familiar form. And that's, if you like, and that's another way of checking that indeed it is of this algebraic form, that there are no derivatives of the vector v here. Oh, this vector v is the w there, of course. So there's no derivatives of this coming in. But actually, if you know that there's no derivatives coming in, then when you write this all out, you can just drop those derivatives because you know that they have to cancel in the end. So it makes the calculation not very long. And you get the answer is this. Alpha, beta, gamma, delta is equal to, okay, anti-symmetrized and gamma delta of the following thing. It involves two derivatives of the metric, but one derivative of the Christoffel symbol. And then another combination of the Christoffel symbols. One way you can remember what's going on here is, well, the gamma and the delta, they belong to the derivatives. So it's this index that belongs to the derivative in the Christoffel symbol, and this is a derivative, a partial derivative in the coordinate frame. And then there's left over alpha and beta. The sign, of course, is purely conventional, and people sometimes use the opposite sign. But if we use that convention, then we get, if we use all the conventions we've used for defining gamma and so on, then it comes out like this. And the second one sort of resembles, might remind you of the homework problem a little. This resembles what you would get if you imagined this to be in some way a covariant derivative, which it's not. But if you imagined it to be a covariant derivative, then one of the terms that you'd get in expanding out the covariant derivative of the Christoffel symbol would be this term. So that's one way of remembering the structure of the... It's the one that you would get from working with the covariant, with the contravariant index. Okay. Anyway, that's just a mnemonic device. So that's the expression. And another interesting thing to note about this is that, remember, the Riemann tensor, I mean, it gives us the Riemann tensor in the form we originally got it, with one index up and the other three down. And so the symmetry, the full symmetry of the Riemann tensor is not actually manifest in this. You have to do a little work to show, if you start with this, that it has that extra bit of symmetry. Namely, this bit is manifest, but this part is not manifest. Okay. Gesundheit. So yeah, that's about Okay, so I think that's really most of what I intended to say about the Riemann tensor and the Ricci, the tensors made from it, the Ricci tensor, Ricci scalar, and Weil tensor. So I should stop. Are there any questions on this? So the next topic is the gravitational action. Which corresponds to section 8.1 to 8.2 in Schutz and section 4.3 in Wald. So as I've been saying, the most important thing that the Riemann tensor can do for us is give us, well, of course, it'll give us, through the Ricci tensor, it'll give us the Einstein equations, but the sort of modern way of looking at it is it does that by giving you the gravitational action, and then the field equations come from varying the gravitational action. So of course, the action, if you, maybe I'll go through this. Let me just write it down for a second. So this is the action over some region of space-time. We won't necessarily take it to be the whole, which I'll call this curly X or whatever this. I'm not ever quite sure what the name of this symbol is. But so the action of that region of space-time is equal to 1 over 2 kappa times the integral over that region of r dv minus the cosmological constant times the integral over the same region of dv. In other words, it's just the volume of that region plus possible surface terms, that boundary terms that are integrated over the boundary of that region, where, as always, this kappa is 8 pi g. So dv dv we've defined before, but we never gave it a sort of proper intrinsic definition. We define, if you remember how we defined it only in terms of a coordinate system. It actually just really geometrically does mean volume. And the equation that you write down for it, which is dv equals root minus g times d4x, this actually can be thought of as the product of two covariant objects, this root minus g and this d4x. Both of these are, however, what are called tensors with density weight, or tensor densities, which we haven't discussed. There's some sort of mild generalization of the notion of tensor. If you do that, then you can define this determinant. I mean, then everything here is truly a geometrical object. But since we haven't discussed that yet, you could, if you want to make some precise notion of what it is in your mind, if you want a formula for it, then you have to go back to a coordinate system and compute both this and this in the coordinate system. But their product, of course, is independent. We checked that their product, this dv, which corresponds to a little infinitesimal region of the manifold, that's independent of the choice of coordinates, and that's just a scalar. So we're integrating a scalar with respect to a geometrical volume element over the manifold. Now, I wanted to say, let me just shortcut this. So I wanted to say something a little bit on the motivation. Where does this expression, come from for the gravitational action? And for that, I wanted to say a little bit about the dimensions. There's obviously not going to be time to do that. So let me just you can check what the results are. The main result is just very intuitive, which is that the dimensions of the Ricci scalar are length to the minus 2. That's what you would expect, because the Ricci scalar involves, the Riemann tensor, involve, whereas the formula, it involves the derivative of gamma, but gamma involves the derivative of the metric. So gamma has two derivatives in it, so you would expect that the Ricci scalar, which is just a contraction of the Riemann tensor, which has two derivatives, would also have two derivatives in it. I mean, it does have two derivatives in it, and therefore you would expect it to have dimensions of minus 2, which it does. When we come to write, now we might ask, what's the dimensions of this kappa? When we come to write the action, well, remember that h bar is known as the quantum of action, so you can always remember what is the dimensions of action by whatever the dimensions of h bar is, and that if we set c equals to 1, like we're always doing, then we have only really two independent dimensions, a mass and a length, or a mass and a time. So I'll take it a mass and a length. You can easily work out that the dimensions of h bar are a mass times a length. And of course, the dimensions of dv are, it's the length to the fourth volume. So if you were plug that in and you say, what is the dimension that the gravitational constant should have, this rationalized gravitational constant, then you find that it's a length divided by a mass. And for lambda, so this is just a mnemonic device to remember the dimensions of action. For lambda, it's even simpler. You want this to have, I mean, if you work it out again, you'll find that it has a mass divided by a length cubed. That's why some people think of it as a kind of energy density, because it has the same dimensions. And it looks in the Einstein equations, as you'll see, as being a kind of perfect, it looks as if it were a perfect fluid with that energy density in its rest frame of lambda. So, what do I want? So there's a sort of dimensional, hand-waving dimensional analysis that goes along with this that tells us what we would expect, whatever that means, the values of these constants to be. And that's the first strong indication of the so-called cosmological constant puzzle or problem or something. Catastrophe or something, which is that it comes out way wrong. It's all hand-waving, but it's the kind of way that people think about it. They think, first of all, you notice that in ordinary unit. Oh, so I wanted to say, so in the context of a full quantum theory, so quantum gravity and quantum field theory, if we set h bar equals to 1, then of course, as you know, a length looks like an inverse mass, as you see right here. That means that this kappa looks, in that case, we can just keep length as our only dimension, and then we can say that kappa looks like a length squared, known as the Planck length squared. Right? So we call that the Planck length. And the fact that the gravitational constant in ordinary units is so small in the sense that the gravitational force between between this eraser and this paper is much, much less than electrostatic forces and so on, and in an atom and so on, the forces between electrons and nuclei are much, much bigger. In that sense, this kappa is a very small number, and of course, it turns out to be about 10 to the minus 32 centimeters if you set it to 1. So this suggests that there's some fundamental length in physics, which is around 10 to the minus 32 centimeters, and the value of kappa is reflecting that. So in causal sets, it would be the discreteness scale, the fundamental discreteness scale. But then if you use that same reasoning for lambda, what do you get? Well, now it's, again, we can trade the mass for an inverse length. So it becomes 1 over length to the fourth. This is if h bar is set to 1, thinking of quantum gravity. Now we get 1, this was, this gravitational constant was a small number squared, which is small, even smaller. But this cosmological constant is 1 over a small number to the fourth. So it's some huge, if we take the same, if we say that the value of kappa is reflecting some fundamental length, then why doesn't lambda also reflect that fundamental length? If it does, then it comes out, as you will have heard many times, around 120 orders of magnitude bigger than the actually observed cosmological constant. So that's the mystery of the cosmological constant. There's nothing inconsistent about it, but it's very mysterious from many points of view. And what makes it more mysterious is that it's not zero. I mean, you could imagine, well, there's something that we don't understand yet that sets it to zero. That's easy to imagine, although it's not easy to come up with what that thing is. But it's much harder to imagine that there's something that we don't understand yet that sets it almost to zero, to a precision of 1 part in 10 to the 120, but not quite zero. So that's a sort of that's this numerology for the values. I mean, so I should say this action that we've written down has 2 free parameters, and this is some numerology of setting, wondering about why the parameters are the way they are. But then, why they are as they are. But another question is, where do we get this form of the action from in the first place? Why did we write this down and not any innumerable bunch of other things? So I wanted to say a little bit about that. So we want to we start off with the assumption that we want to form the action by an integral of some local scalar, which the Lagrangian. If you do this, then you'll be guaranteed that the variational equations that come from this are local equations. So if you want that, we're doing classical physics now. So if you want partial differential equations, which are local objects, then this is the natural form to take for the action. If you want, so that leads to some partial differential equations, the Einstein equations for the gravitational dynamics. If you also want second order equations, then you can't have too many derivatives. I mean, this still leaves a huge amount of freedom. We could have 12th derivatives in this, and we could have non-analytic functions and all kinds of things. But if you want only second order equations, because maybe you're thinking that the Newtonian physics has second order differential equations and Maxwell's equations are second order. So let's say you don't want, and then there are various pathologies associated with higher order equations like instabilities. And so say we want a stable ground state. By ground state now I just mean Minkowski space, which we now know is stable, although it took decades to prove this. So the second, if we want those things, then that leaves us very little freedom. It basically limits us just to this and this. And of course we want, I didn't even say this, but we want lambda to be a scalar. We want it to be background independent or some, in other words, we should be able to write so it's a scalar depending on the metric only. Again, you might ask, why is that supposed to be? But it all comes from natural, they're all plausible generalizations of what you knew. So Maxwell's equations have that character, that the action is just a term depending purely on the electromagnetic potential, plus terms that couple it to the charged matter. So you might expect gravity to be a term depending just on the metric plus a term coupling the metric to matter. You might also remember that in the Newtonian, the sort of baby field theory for Newtonian gravity, where this is the gravitational potential, it looks like Laplace. Whose equation is this? Anyway, someone's equation. Poisson's equation. Anyway, this equation. It looks like that. That's a term involving only gravity and so on, which you would expect, you would want that to come out of the gravitational term in the action. Of course, I should have put here, this is the gravitational action. I haven't put the matter in yet, the non-gravitational matter. So that's another motivation. This motivation that it should depend only on the metric, not depend on the coordinates in particular, is what you might call general. It's closely related to what we call general covariance. So it's the combination of the statement that it should be a true scalar. It should be so that the action should be unchanged under diffeomorphisms, and the action should depend on the metric. If you put all those conditions, another reason you might want second order as well. That's the first thing to try. It's simpler than higher order equations. Higher order. Many people are thinking about these higher order equations now, but from all those points of view, and there's some sort of another kind of motivation based on dimensional analysis called effective field theory way of looking at it. Basically, just as a dimensional analysis that we just went through here. And all of those things will tell you that the first two terms, that all the terms beyond this perhaps you can neglect. So in particular, these are the only terms you can write down that'll lead to the second order equations. Also, of course, you want the correct Newtonian limit. That you have to then go back and see whether it checks, which it does, of course. Another question is why we want an action principle at all. That's a very hard one to answer, but I think one possible answer is, aside from the fact that it seems to have always worked for the other fundamental theories, the other answer is that it seems to be, if you think this is really in the end some classical limit of a quantum theory, then, and if you think of quantum theory in the path integral way, then you need this thing to go into the amplitude for the path integral. So there has to be something like an action. That's all. And then there's a kind of implicit condition here. There's two things. If we don't specifically demand second order equations, then there's two other things that we've demanded here, which is that we just put simple polynomials in the Riemann, in these Ricci scalar, and so on. But if you, it's what you might call an analyticity. But if you drop this, you can write all kinds of strange things. Like you could write Ricci to the -3. And you could write an action like this. This is local. Depends only on the Ricci scalar and so on. People do consider, I don't know if this exact one has ever been considered, but recently there's a lot of work in considering modified ones, all related to this cosmological constant mystery, most of it. But we don't consider those. This is not, what is it? It's not holomorphic or analytic because of this funny pole that I've put in it at r equals 0. Or you can consider non-local things, or you consider higher curvature. These are even more popular, with some sort of squares of Riemann and Ricci. Or you can consider non-local things. See, if I put the square outside, then I really have something that's non-local, because if you think when you take the variational equations, it'll relate the Einstein tensor, which comes from varying this r, to some sort of integral over the whole space-time. If you vary this has the Ricci tensor has Ricci scalar has two derivatives. So you might have naively expected when you took the variational equation, you'd get 4 derivatives. And you would in this case. But in the specific way where it enters linearly, you only get 2 derivatives, which is a bit of a miracle Although it's easy in retrospect to understand where the miracle comes from. So you just barely got away with second order equations by using this action. Okay, so I think I'll quit there. The next thing is to discuss, to actually go through and vary the action and show how the Einstein equations come out. Yeah.
I read an argument once where they said that because